Welcome to my video tutorial Excess Burden on Labor Income Tax in General Equilibrium. This is the second tutorial in a row on the study of the excess burden of a labor income tax. The first one was on partial equilibrium, which considers the material covered in section 5.3.1 in my book on public economics. Now this part here will look at the general equilibrium effects of a labor income tax, and we will study the material of section 5.32, which you can also download from my homepage. So let's get into the slides which are available on my homepage, and let's go to the section on labor income tax. And we click through to get to the general equilibrium analysis. So why do we study general equilibrium? Now, in the previous part on the partial equilibrium, we assumed that wages stayed constant. So this will not be the case, of course, in a general equilibrium. Consider the effects of a labor income tax tau L on labor supply L. Well, if the substitution effect is higher than the income effect, households will reduce their labor supply, and as a consequence, total output and total income will go down. And with lower income, households will also reduce savings. So as a consequence, they will invest less and the capital stock will go down. And therefore, we will have a lower equilibrium wage. And this effect is not considered in the previous partial equilibrium analysis. So the most convenient model to study general equilibrium effects, of course, is the Ramsey model. So the Ramsey model is very convenient in a way that we have a micro foundation, so that we have endogenous labor supply and endogenous savings. We have utility maximization, so which allows us to conduct a welfare analysis, just comparing utility prior and after the change in taxes. And of course, we have the general equilibrium effects here as savings affect capital accumulation. So we assume that households maximize discounted utility, so that utility is time separable, and instantaneous utility in each period t is discounted by the factor beta, which must be smaller than 1. Instantaneous utility is a function of consumption C and labor L. And for convenience, we will just look at the Cobb-Douglas case. So C to the power iota times 1 minus L to the power 1 minus iota to the power 1 minus sigma over 1 minus sigma will be our utility function as specified in equation 5. So 1 over sigma is our intertemporal elasticity of substitution, which measures our reaction to a change in the interest rate. So if the interest rate goes up by 1 percentage points, our consumption in the next period, CT plus 1, relative to consumption in this period, CT, increases by 1 over sigma. So if 1 over sigma is high, it means that consumption growth increases a lot, meaning that we reduce consumption today by a larger portion and increase consumption tomorrow by a higher portion, so that savings react more sensitively with respect to a change in the interest rate. Iota and 1 minus iota are the relative weights of consumption in leisure in utility. The households accumulates capital stock KT plus 1. It increases with investment IT, which will be equal to savings, and capital depreciates at the rate delta, which reduces our capital stock. Now the household budget constraint is given by equation 7. On the left-hand side, we have income. Income is labor income, WLT, where WT denotes the wage rate, and our gross wage income is taxed at rate tau L. We also receive interest, income, RT/KT, and we spend it on consumption and savings again are equal to investment or to the increase in capital stock. The first order conditions for this utility maximization are provided by equation 9a, b, and c. 9e is the first order condition with respect to consumption, so the marginal utility of income, while lambda t is equal to the marginal utility of consumption, the right-hand side. According to equation 9b, the optimal labor supply is chosen such that the marginal utility from working an extra unit, an extra hour, is equal to the loss in utility from decreased leisure. So on the left-hand side, we have the increase in income, 1 minus tau L times W by working an extra hour. And this provides us with marginal utility lambda t. And on the right-hand side, we have this utility from having a loss of leisure by 1 unit. 9c is our Euler equation, also called our Keynes-Ramsey rule, on the left-hand side, which gives us the optimal decision with respect to savings. So it's the first order condition with respect to capital K t plus 1, capital stock in period t plus 1. On the left-hand side, we have the marginal utility of consumption. So if we spend 1 unit today, we get this extra utility, lambda t. If we save it, our return is equal to 1 plus RT plus 1 minus delta at the end of period t plus 1. This provides us with extra utility lambda t plus 1, which, however, we have to discount by the factor beta to make it comparable to the present utility. And equations 9a and 9b together imply our first order condition with respect to consumption and leisure. Our expenses on leisure, which are equal to the numerator on the left-hand side, 1 minus tau L times W times 1 minus LT. Notice that the opportunity cost of leisure are WT times 1 minus tau L. Relative to our consumption spending, CT, which is the denominator, is equal to the weights in utility 1 minus iota relative to iota. So, as we know from a Cobb-Douglas utility, we spend our total endowment with income, 1 minus tau L W, on our two goods, leisure and consumption, at the shares 1 minus iota and iota respectively. We assume that good markets and factor markets are characterized by perfect competition, and we have Cobb-Douglas production technology. So yt is equal to k to the power alpha, L to the power 1 minus alpha, as presented by equation 10. So we have constant returns to scale. We have perfect competition, so that wages and real interest rates, the two factor prices, are equal to the marginal products of labor and capital according to equation 11a and 11b. So together these conditions imply that the Euler theorem holds, so that total production is equal to total income in the form of wage income and interest income. The government runs a balanced budget, so the total government expenditures G are equal to tax revenue tau L W L. In our model, government expenditures are pure waste and will neither affect utility nor production. This will be the topic in a later section of this chapter. Now, if we insert equations 11a and b, the factor prices and the government expenditures G, into our household budget 7, we derive the resource constraint of the economy, which is given by equation 13. So total production is equal to total demand, and demand is equal to consumption, private consumption, plus public consumption, plus investment, and investment is simply equal to the increase in the capital at stock plus depreciation. Now we have to calibrate our model so that we can compute numerical estimates of our welfare and general equilibrium effects of a labor income tax. So we choose the average labor income tax tau L that we observed in the United States over the last 50 years, which is equal to 23%. This is an estimate by Gom and Ravi Kanwar. We use a discount factor beta of 0.96, so implying a discount rate of 4%, so that our real interest rate minus depreciation is approximately 4%, and a value that is often used in general equilibrium studies as real interest rates have been approximately 4% over the last 40 to 50 years. Now, our depreciation rate is equal to 10% as in the US economy. Our labor income share is 64%, so this translates into alpha equal to 36%. So this labor income share of 64% is a little bit higher than observed recently in the US economy. So over the last 50, 60 years, the labor income share has declined from 62% in 1965 to 57% today. So our value is a little bit higher, but we use this value in accordance with the general equilibrium literature in this field. We also set the intertemporal elasticity equal to 1/2, implying sigma equal to 2.0. And we calibrate iota so that the labor supply is 0.3 or 30% in the steady state. This amounts, our calibration implies tax revenue equal to about 14% of GDP, so this will be equal to our government expenditures as well, as we assume a balanced budget. Now the computation is carried out in Chapter 5 welfare tau L point G, or also in the MATLAB program, Chapter 5 welfare tau L.m, and we will describe it in more detail in the next video. But let us turn to the results and the effects of a marginal increase of the labor income tax by 1 percentage point, so from 0.23 to 0.24. First, we look at the partial equilibrium effect in this Ramsey model. So we assume that the wage rate remains fixed. Of course, this is counterfactual, and we will estimate the effect of this assumption when we look at the general equilibrium effects. Now we can compute the new optimal labor supply from the first order condition with respect to the labor supply, which is the first equation here, and the implied labor supply is L equal to L prime, and the new labor income tax is tilde tau L for 24%. And with the help of the budget constraint, we can assume, we can compute the consumption C prime, and we assume that the household keeps capital stock constant and spends all labor, net labor income and interest income on consumption, which is provided by the second equation on slide 35. So this is a simple numerical problem. We can even compute it with the help of a pocket calculator. So the old equilibrium, the steady state, is characterized by labor supply equal to 30%, implying consumption C equal to 0.3 or 3. And in the new equilibrium, these two values amount to 0.2994 for the labor supply L prime and 0.2998 for consumption C prime. Now, to compute the consumption equivalent change, we look at the equation, the first equation on slide 36. So by how much should we increase or decrease the consumption and in the old steady state, so that the labor supply, that the utility, that the utility is equal to the utility observed in the new equilibrium with the higher tax. We can compute this delta by looking at utility in old and a new steady state, as presented by the second equation here, and we find it to be equal to minus 1.07%. So instantaneous utility declines by an equivalent of a decrease in consumption of 1%, 1.07% in the old steady state. Now, with the help of this consumption equivalent change delta, we can compute the deadweight loss. The deadweight loss is the difference between the consumption loss, so 1.07% of consumption C in the old steady state, amounting to 0.003244, and the additional tax revenue. The additional tax revenue are the new labor income tax tilde tau L times the new labor supply L prime times the wage rate W, which we assume to be constant, minus the old labor income tax is tau L times W, and this amounts to 0.00310. So the difference between the loss in consumption and the tax revenue amounts to 0.000144. And relative to the tax revenue, this amounts to 4.7%. Observe this, that this is really close to the number we calculated for our rough estimates of the deadweight loss relative to revenues in partial equilibrium, where we use a heuristic estimate, and you can see here for 25% it's equal to 5% deadweight loss relative to revenues, and here in our Ramsey model the partial equilibrium effect is 4.7%. So these two are really close. While the former was one where we looked at the average deadweight loss relative to average tax revenue, in this case we looked at the marginal effect, so be careful to compare these two. Now let's look at the general equilibrium effects of an increase in tau L from 23% to 24%. Now wages and interest rates are endogenous, so when tau L increases, we will find that our labor supply declines from 0.30 to 0.2995. And as a consequence, we have lower income, we have lower savings, and therefore the equilibrium capital stock and the steady state capital stock are also lower, and so will be wages. Consumption falls to 0.2998, which implies an individual's welfare loss equivalent to delta, to consumption equivalent change delta of 1.10%. We can again compute tax revenues and the deadweight loss, which is now significantly higher. It amounts to 0.000213. And our deadweight loss relative to tax revenue is now 6.8%. So if we compare this to the partial equilibrium effect, where it was 4.7%, we see an increase in the deadweight loss, and this results from the general equilibrium effects, from the effects of lower labor supply on total income and hence on total savings and the capital stock. Now in this table we find, you also find other marginal deadweight loss relative to tax revenue estimates for different tax rates tau L, ranging from 10, 23, 40, 50, and 59%. We chose these values because there are prominent in the literature. So, for example, Prescott estimates that the tax wedge in the United States, the income tax wedge, is 40%. So in this case, the deadweight loss amounts to 16.4% of revenues. Now look at poor Germany. In Germany we have much higher labor income taxes, especially due to the high social security contribution rates. So our tau L amounts to 50.9%, and in this case the deadweight loss is much higher, 54% relative to revenues. Now, so far we have only looked at the steady state, and this is a little bit simplifying. In doing a thorough welfare analysis, we also have to consider the transition dynamics. And the transition dynamics for our economy are illustrated in the next figure. So here we assume that until period 0, the tax rate on labor income tau is equal to 23%. Now, in period 0, there's an unexpected increase of tau L to 24%, and as a consequence, you can see that labor supply drops, and therefore total income drops, and we reduce our savings over time, and so the capital stocks starts to shrink until it reaches its new long-run equilibrium after 30 to 40 periods. This change in labor supply and capital is also reflected in production. So first we have this high decline in production because labor supply adjusts instantaneously, while the capital stock only adjusts over time and slowly reduces to its long-run equilibrium. Tax revenues, on the other hand, increase because of higher income taxes and then remain rather flat, but let me tell you, they overshoot the long-run equilibrium by a small amount. This is because we still have high capital stock and high wages during the transition, so there will be a little bit higher tax revenue during the transition as well. Now, how do we adjust consumption? Well, we smooth consumption intertemporally, so after we have realized that our net income is reduced drastically after this increase in taxes, we spread out our consumption rather smoothly and take into account that our wages are still declining due to the decline in capital stock, and we also substitute labor intertemporally as illustrated in the upper right panel. Now, how does this affect our transition, our welfare? Well, utility during the transition is in fact higher than in the new steady state. First of all, our consumption, as you can see in the second right panel, in the middle right panel, is higher initially than in the new steady state, and labor is lower in the beginning of the transition than in the long run, and this means vice versa, that leisure is higher in the beginning of the transition. So both arguments of the utility function, consumption and leisure, are higher in the initial phase of the transition and lower in the new steady state, and therefore utility is also higher in the first periods of the transition, and therefore our consumption equivalent change over the whole period is only 1.07% and not 1.1%. So these consumption equivalent changes, which include the consideration of the transition period, are also included in the table on slide 38. And as you can see, if you compare the steady state effect and the transition effect, the consumption equivalent changes are somewhat smaller here in this case. Now, this concludes the video here on the general equilibrium effects, we have found that the deadweight loss relative to tax revenue is higher in general equilibrium. We have found substantial deadweight losses for the United States and particularly for Germany, where they are even in excess of 50% of revenues. And in the third video in this series of welfare effects and distortionary effects of labor income taxation, we will consider the computation of these effects. So, looking forward to see you in the next video.